For around $100 in materials, you can build a backyard solar system that captures up to 70% of the sun's energy as usable heat, stores it overnight in a barrel of water or a bucket of sand, and outperforms a $20,000 rooftop array on every metric that matters. Yet across the United States, where 4 million homes now have rooftop solar, almost no one has ever heard of it. This is the parabolic solar trough, and this is the story of the ancient mathematician who proved the principle, the Philadelphia inventor who built the first commercial plant in 1913, and why the energy industry has spent 50 years selling you the less efficient version. The parabolic trough is not a modern idea. The curve at the heart of it is one of the oldest pieces of applied geometry humanity ever discovered, and it was being used as a weapon of war more than 2,200 years ago. In 212 BC, during the siege of Syracuse, the Greek mathematician Archimedes was tasked with defending his coastal city from an invading Roman fleet. According to the historians Lucian and Anthemius of Tralles, Archimedes assembled rows of polished bronze shields along the city walls in a precise curve. When Roman ships approached, his soldiers angled the shields to focus the noonday sun into a single point on the wooden hulls. The ships, sealed with pitch and tar, ignited and burned. Historians have argued for centuries about whether this actually happened. But in 1973, a Greek scientist named Dr. Ioannis Sakas decided to settle it. At the Skaramagas naval base outside Athens, he lined up 60 Greek sailors holding bronze-coated mirrors and aimed them at a tar-covered plywood ship 160 ft away. The ship caught fire within minutes. In 2005, an engineering team at the Massachusetts Institute of Technology repeated the experiment with 127 mirror tiles aimed at an oak fishing boat. The boat ignited in 10 minutes. Concentrated sunlight could reach temperatures hot enough to ignite wood, melt metal, and as it would later turn out, boil water hard enough to power an industrial civilization. The Chinese were doing it independently with concave bronze mirrors called yang sui to start ritual fires as early as the Western Zhou dynasty around 1000 BC. Priests held the mirrors out at noon and used the focused light to ignite sacred altars. The Romans, a few centuries later, built south-facing glass walls and polished metal reflectors into bathhouse architecture so consistently that the architect Vitruvius wrote a treatise on it in the 1st century BC. By the medieval period, the technology slept. But in 1774, the French chemist Antoine Lavoisier built a 4FT glass lens in the gardens of the Royal Academy of Sciences in Paris that focused sunlight hot enough to melt platinum at 3,200 ref, the highest man-made temperature on Earth at the time. 3 civilizations in 3 millennia, separated by thousands of miles, all arrived at the same insight. A curved reflective or refractive surface could turn diffuse sunlight into something approaching the power of fire itself. The curve they were all using has a name, and in 1913, a Philadelphia inventor would build the largest one anyone had ever seen in the middle of the Egyptian desert. Frank Schumann was a glass and engineering inventor from Tacony, Philadelphia. He had spent 2 decades building solar engines in his backyard, convinced that within 50 years, humanity would burn through every accessible coal deposit on the planet. His first prototype in 1907, built behind his own house, was a wooden box filled with iron pipes containing ether, which has a boiling point of just 95 bar-F. The ether vapor, expanding under the sun, drove a 3 and 1 to 2 horsepower steam engine that ran continuously through the Philadelphia winter, drawing crowds of newspaper reporters. By 1911, with backing from British and German investors, Schumann partnered with physicist Charles Vernon Boys and traveled to Madi, a farming village on the Nile south of Cairo. The goal was simple: build a solar plant powerful enough to irrigate the desert. On a blazing June day in 1913, in front of journalists, civil servants, and Viscount Horatio Herbert Kitchener of Khartoum, the most powerful man in colonial Egypt, Schumann switched on the world's first commercial solar thermal power plant. 5 parabolic troughs, each over 60 mm long, lined with mirrors and tracking the sun across the sky, focused sunlight onto cast iron boilers running down the center of each curve. The water inside reached 200 °F. Steam roared into a custom-built engine. The engine pumped 23,000 L of water per minute out of the Nile, soaking the surrounding cotton fields. Schumann had proven, in front of the British Empire, that you could run a working industrial machine on nothing but sunlight. Scientific American called it the dawn of a new energy age. Schumann was already sketching a 20,000 square mile plant in the Sahara that he calculated could power the entire world. Then, in 1914, World War I began. The British Army dismantled the Mahdi plant for raw materials. Schumann died in 1918 before he could rebuild. By the 1930s, cheap oil from Texas and the Persian Gulf had buried the idea of solar power for 40 years. The technology was rescued by the 1973 oil embargo when the price of crude quadrupled in 6 months, and the United States Department of Energy was forced to revisit every alternative energy source it had abandoned. Engineers at Sandia National Laboratories in Albuquerque pulled Schumann's 1913 designs out of the archives and began modeling them with modern materials. By 1979, they had a working test loop in the New Mexico desert, producing steam at over 600 degrees Fahrenheit. 5 years later, that loop became the basis for the largest solar power plant the world had ever seen. To understand how, you have to understand what a parabolic trough actually does, because what it does is something a photovoltaic panel physically cannot. A parabolic trough is a piece of math made physical. A parabola is a curve where every point on the surface reflects an incoming parallel ray to one identical focal line above it. No other shape in geometry does this. A circle does not. An ellipse does not. Only a parabola. When you align a trough toward the sun, every photon striking the mirror is bent toward the same narrow strip of pipe running down its center. The light is not just reflected, it is concentrated. A single square meter of mirror delivers the sunlight of 40 or 50 square meters onto that pipe. The pipe gets hot, not warm, hot. Industrial troughs reach 750 degrees Fahrenheit on a clear afternoon. A backyard build using polished aluminum and a black-coated copper pipe reliably reaches 300 to 400 degrees, enough to boil water, cook food, sterilize medical equipment, and run a small steam engine. The pipe at the focal line is called the receiver, and it is the second piece of clever engineering. A high-performance receiver is a black-coated steel tube wrapped in a glass envelope with the air between them pumped out to form a vacuum. The black coating absorbs 96% of incoming sunlight. The vacuum eliminates convective heat loss, the same principle as a thermos flask. This matters because of a physics rule called the Stefan-Boltzmann law, which says that as an object gets hotter, it radiates heat away to its surroundings at a rate proportional to the fourth power of its temperature. Without the vacuum jacket, a 400-degree pipe would radiate so much heat back to the air that it could never get any hotter. The vacuum is what lets the temperature climb. It is the same principle that makes your insulated coffee mug hold its heat for hours. The third piece is the tracking. A fixed mirror only points at the sun for a few minutes per day. A parabolic trough is mounted on a single-axis tracker, usually a small DC motor driving a screw or a chain that rotates the trough from east to west across the sky at 15 degrees per hour to match the rotation of the Earth. The motor draws less power than a desk lamp. With tracking, the trough collects useful heat from sunrise to sunset, 6 to 10 hours a day depending on latitude. A backyard tracker can be built for under $20 using a windshield wiper motor and a simple photodiode controller. And this is where the parabolic trough begins to embarrass the silicon solar panel. A photovoltaic panel works by knocking electrons loose inside doped silicon. The maximum theoretical efficiency of a single-junction silicon cell is governed by the Shockley-Queisser limit, which caps conversion at around 33% under perfect laboratory conditions and around 22% in any panel you can actually buy. The remaining 80% of the sunlight is wasted as heat the panel must actively shed to keep functioning. In fact, every 10 degrees Fahrenheit, a silicon panel rises above 77 degrees in ambient temperature. Its output drops by another 0.5%. The hotter the day, the worse a solar panel performs. A parabolic trough does the opposite. It captures that heat as the entire point of the system. The hotter the day, the better the trough works. Real-world thermal efficiency for a well-built trough ranges from 50 to 80% of incoming solar energy converted into usable heat. That is 3 to 4 times the efficiency of the panel on your neighbor's roof, achieved with 2 pieces of bent metal, a pipe, and a coat of black paint. And that all sounds impressive, But how does it actually compare to a battery in a basement? This is where the second collapse of photovoltaic logic happens. Efficiency is only half the advantage. The other half is storage. A solar panel produces electricity only when the sun is shining, which is why every home solar installation must be paired with either a $15,000 lithium battery or a grid-tie net metering agreement that has been progressively gutted by utilities in over a dozen U.S. states. The parabolic trough produces heat, and heat is one of the easiest forms of energy on Earth to store. A barrel of water has a specific heat capacity of 1 calorie per gram per degree Celsius, the highest of any common substance. A 200-liter drum of water heated to 140 degrees Fahrenheit holds roughly 12 kilowatt-hours of usable thermal energy, the same as a Tesla Powerwall, for less than $30 in materials. Sand stores less per kilogram than water, but tolerates much higher temperatures and stays hot for weeks. Molten salt holds its temperature for days. In Kankanpää, Finland, a company called Polar Night Energy built a steel silo filled with 100 tons of sand heated to 500 degrees C that holds 8 milliliters of usable thermal energy and supplies an entire district heating network through the Finnish winter. In June of 2025, the same company commissioned a second silo in Pori with 2,000 tons of crushed soapstone, delivering 100 megawatt-hours of storage. Both systems use the same physics a homeowner can use in the backyard with a barrel and a roll of insulation. So, how does this compare to something more relatable? In 1984, an oil shock and a federal tax credit drove a consortium of engineers into the Mojave Desert outside Daggett, California, to build a commercial solar thermal plant called Solar Energy Generating Systems, or SEGS. By 1990, SEGS had grown to 9 plants across 3 sites with a combined capacity of 354 megawatts. The complex contains 936,000 parabolic mirrors covering 6 and 1/2 square kilometers of desert. Lined end to end, they would stretch 370 kilometers. SEGS ran continuously for over 30 years, was the largest solar plant of any kind on Earth for 3 decades, and used the same geometry Archimedes used in 212 BC. The second proof came in 2013 in Gila Bend, Arizona. The Spanish company Abengoa Solar built the Solana Generating Station, a 280-megawatt parabolic trough plant with 3,200 trough collectors stretched across 1,920 acres of desert. Solana was the first U.S. solar plant of any kind to integrate a true thermal energy storage system. 12 massive molten salt tanks, each 140 FT across, holding enough heat to keep the plant running at full capacity for 6 hours after sunset. Solana powers 70,000 homes in the Phoenix metropolitan area. It runs while the moon is up. A photovoltaic plant cannot do this. A photovoltaic plant goes dark the moment the sun sets. But perhaps the most striking proof is not industrial at all. It is religious. At the Shirdi Sai Baba temple in the Maharashtra state of India, 73 parabolic reflectors mounted on the temple kitchen roof concentrate sunlight onto a network of steam boilers that feed an industrial cooking facility preparing hot meals for 20,000 devotees every single day, 300 days a year, with no fossil fuel input on sunny days. The installation, designed by German engineer Wolfgang Scheffler in 1986 and replicated across dozens of Indian temples, hospitals, and schools, has reduced LPG consumption at the Shirdi site by over 100,000 kilom per year. At Mount Abu in Rajasthan, a similar system at the Brahma Kumari Spiritual Center cooks for 35,000 people per day. These are not pilots. These are operational 20-year-old food production systems running on bent aluminum and sunlight. And the most relevant proof is not industrial or institutional at all. It is the backyard. A Canadian engineer named George Plasek documented his own build in 2010 in a manual titled The Solar Parabolic Trough Concentrator Home Experimenter's Manual, with a total bill of materials under $100. His prototype reached working temperatures above 300 degrees Fahrenheit on clear days and ran his domestic hot water for an entire summer with zero grid input. Engineers in arid regions of India, Mexico, and Kenya have built community-scale troughs from old satellite dishes, scrap printing plates, and aluminized mylar, each producing enough heat to run a steam pasteurizer or a small refrigeration cycle. In Lesotho, the Solar Cookers International Field Team documented village-scale parabolic units, sterilizing medical instruments at rural clinics where the nearest grid is 40 kilometers away, materials cost is consistently between $50 and $300. So, if a parabolic trough is older than concrete, 3 to 4 times more efficient than rooftop solar, cheaper than a single high-end smartphone, and proven at every scale from a backyard prototype to a 354 MW power plant, why hasn't it become the standard for residential energy in the United States? The answer is that the entire architecture of American solar incentives was built around the photovoltaic panel and around nothing else. The federal solar investment tax credit, originally passed in 2005 and renewed through the Inflation Reduction Act, allows homeowners to deduct 30% of the installed cost of a solar electric system from their federal taxes. It applies to silicon photovoltaic panels, lithium battery storage, and grid tie inverters. It does not, in any straightforward way, apply to a homeowner who builds a parabolic trough that produces heat instead of electricity, because heat cannot flow through an inverter or be sold back to the utility under net metering rules. The Solar Energy Industries Association, the trade body that lobbied the original ITC into existence, has over 1,000 corporate members, almost every one of them a manufacturer, installer, or financier of photovoltaic equipment. There is no equivalent association for solar thermal homeowners. The National Electrical Code, written by the National Fire Protection Association and adopted by nearly every U.S. municipality, dictates every wire, conduit, and disconnect in a residential photovoltaic installation, creating an entire certification industry of UL-listed components and licensed installers. There is no equivalent code for residential solar thermal, which means no streamlined permit pathway, no certified installer base, and no financing product. The mortgage appraisal system, governed by Fannie Mae and Freddie Mac valuation guidelines, recognizes rooftop solar arrays as adding measurable home value of around 4% per kilowatt installed. A homemade parabolic trough is, in most appraisal districts, considered an unpermitted outbuilding. The regulatory framework is structured around the assumption that all home-generated solar energy will eventually flow through the grid as alternating current electricity, and any system that does not flow through the grid is invisible to it, including to the investment tax credit, to state-level renewable portfolio standards, and to the solar renewable energy certificate markets that pay the highest yields per kilowatt hour to rooftop owners. We are told that photovoltaic panels are the modern solution and that solar thermal is a relic of the 1970s. But in reality, the photovoltaic panel is the primitive solution. It captures less than a quarter of the sun's energy, requires rare earth elements mined under exploitative conditions in the Democratic Republic of Congo and Inner Mongolia, depends on a chemistry that degrades by 0.5% every year, and produces a form of energy, alternating current electricity, that no human body or building actually needs in raw form. What we need is heat for water, heat for cooking, heat for space heating, and a smaller amount of electricity for lighting and electronics. The parabolic trough delivers the heat directly at 3 times the efficiency for 1/100th of the cost, with materials a homeowner can buy from a hardware store, and a curve any 6th grader can plot on graph paper. It has been pushed to the margins not because of engineering, but because there is no business model in a curved mirror that you bend in your driveway, point at the sun, and never service again. It is the same succession of failure pattern visible across the entire residential energy sector, where homeowners are sold machines that depend on rare materials, require a grid connection, and degrade on a schedule that ensures a replacement sale in 15 years. So what does a real practical path look like for a homeowner who wants to use this today? There are 2 clear options. The first is a single domestic hot water trough, around 2 millimeters long and 0.5 meter wide, built from a sheet of polished aluminum or stainless steel, bent over wooden ribs cut from a paper parabola template, with a 1-in copper pipe painted with high-temperature flat black coating running along the focal line. Total materials cost runs between $80 and $150 from any hardware store. Pair it with a 200L insulated water tank salvaged from an old electric heater, and you have free hot water from April through October in any continental climate. For winter operation, swap the copper pipe for an evacuated tube collector available from suppliers like Northern Lights Solar and a Precus for around $100 per tube. and the system will produce useful heat at outdoor temperatures down to 10 degree F. The second option is a community or rural homestead build using salvaged satellite dishes, surplus printing plates from a commercial print shop, or commercial mylar film stretched over a plywood frame. These can be paired with a thermal mass storage unit, typically a steel drum filled with sand, gravel, or volcanic rock buried in the ground for insulation. A 2 cubic meter sand store will hold roughly 50 kilowatts of heat, enough to drive a hydronic radiant floor for 2 cloudy days in a well-insulated home. The reference most builders use is George Plasik's Solar Parabolic Trough Concentrator Home Experimenter's Manual, in print since 2010. Solar Cooker International in Sacramento publishes free parabolic templates and Scheffler dish plans online and runs annual workshops in California, Mexico, and Kenya. Companies like Sunmax Solar in upstate New York and Sunmark in Sweden sell pre-built flat plate and evacuated tube collectors for those who do not want to fabricate their own. For larger Scheffler-style community kitchens, the Indian nonprofit Gaudiya Solar publishes installation specs and trains village engineers across South Asia and East Africa. The limitations are real. The system works best between latitudes of 0 and 45 degrees, performs poorly under heavy cloud cover, requires a south-facing yard or rooftop with clear morning to afternoon sun, and asks the user to think in stored heat rather than instant electricity. But once the system is built, it has no service contract, no inverter to replace, no battery chemistry to degrade, and no grid permission to ask for. The mirror does not know what year it is. It will work for the next 40 summers exactly as well as it worked on the first. The parabolic solar trough is a 2,200-year-old answer to a 21st century problem built from sheet metal and pipe, shaped by the same mathematical curve Archimedes used to defend Syracuse. And the modern energy financing system has decided that, because it produces heat instead of grid electricity, it does not exist on any tax credit, any net metering schedule, or any mortgage appraisal sheet. A lot of what we cover sits outside the mainstream, not because it stopped working, but because the conventional systems are easier to subsidize, easier to certify, and easier to sell on a 30-year service contract. If discovering the lost art of self-sufficiency in direct energy ownership matters to you, please subscribe and like the channel. We are unearthing the history they tried to bury. Let's plant the seeds for a self-sufficient future.